We've looked at how gases behave. Now we'll consider why they act the way they do. For example, why do gases expand when we heat them? The kinetic molecular theory is a model that we use to explain the behavior of gases at the molecular level. Kinetic means motion. The kinetic molecular theory first tells us that gases are composed of molecules that are moving continuously and rapidly. And when we say molecules, we mean gas particles, even though the noble gases are monoatomic. So technically, the noble gases are not molecules, they are atoms, but the rules still apply. The second part of the theory states that the combined volume of all molecules in a gas is negligible compared to the total volume of the gas. In reality, gas molecules aren't particularly attracted to one another, and so they move away from each other as far apart as a container will allow. That's why gases are so compressible. We can squish those molecules much closer together so that they take up less space or less volume. Attractive and repulsive forces of gases are negligible. Energy can be transferred between molecules during collisions, but as long as the temperature doesn't change, the average kinetic energy won't change. In other words, these collisions are perfectly elastic. And the total kinetic energy after the collision is equal to the total kinetic energy before they encountered each other. The average kinetic energy of the molecules is proportional to its absolute temperature. So at a given temperature, all of the molecules in the gas have the same average kinetic energy. Absolute temperature is a measurement of the average kinetic energy. So even though we might have gases that have different masses and individually may be moving with different speeds, the average amount of kinetic energy is the same at a given temperature. If we were to double the absolute temperature of the gas, it would also double the average kinetic energy of the gas. So with a mixture of gases and the gas molecules of different masses, because they're at the same temperature, we know they have the same average kinetic energy. They also have the same average speed, but since the individual gases have different masses, they'll be moving individually at different speeds, even though the average speed is the same. Root mean square speed, whose symbol is mu, is the speed of a molecule of average kinetic energy. In this graph, root mean square speed is represented by the dotted line. And you can see that for nitrogen in this instance, the higher the temperature, here the blue line is representing molecules at 0 degrees Celsius, and the red line is representing the molecules at 100 degrees Celsius. At 100 degrees Celsius, we have a greater fraction of molecules at a higher root mean square speed. And root mean square speed is not exactly the same as mean or average speed, but it's pretty close. And as the average kinetic energy of gas molecules in a sample is directly related to root mean square speed, we can express that mathematically as, where m is mass, and mu is root mean square speed. And since mass doesn't change with temperature, an average kinetic energy does increase with an increase in temperature, then the root mean square speed, as well as the average speed of the molecules in the mixture, is going to increase as temperature increases. So let's apply all of this to the gas laws. Boyle's law looked at the relationship between volume and pressure when temperature is held constant. So if temperature is held constant, then root mean square speed doesn't change. But when we decrease the volume of the gas, the molecules are much closer and they're bumping into each other and they're bumping into the sides of the container, and the more collisions you have, the greater the pressure is going to be. If we were to increase the volume, those gas particles are going to have more space, and those molecules are going to have to travel further in order to collide. Fewer collisions, lower pressure. Charles' law describes the relationship of temperature versus volume when we're holding pressure constant. And when we increase temperature, we know we increase the average kinetic energy of the molecules because we're increasing the amount of collisions that the gas molecules have with each other and with the walls of the container. And so if the volume can't change then, the pressure exerted is going to increase due to the increased number of collisions. The kinetic molecular theory tells us that average kinetic energy of any mixture of gas molecules, 1/2 of the mass times the root mean square speed squared, has a specific value at a given temperature. Let's compare helium, a very light gas, with xenon, which is much more massive. As long as both of these gases are at the same temperature, they'll have the same average kinetic energy. But helium, being lighter and smaller, will have a higher root mean square speed, mu, than the heavier xenon. And we can express this relationship quantitatively as, where our root mean square speed will be expressed in meters per second. M is our molar mass. And the units for molar mass are grams per mole. And T is going to be our absolute temperature, so that'll be in units Kelvin. So you can probably recognize that the value for R that we're used to using with the gas laws is not going to work in here because, first of all, there's no mention of any pressure. We've got grams to deal with, as well as seconds and meters. So we have a different value for R that we're going to use in this equation. This value for R is going to give us mass in kilograms, meters squared per second squared, so that will line up for our meters per second for our root mean square speed, and we still have moles and our units Kelvin. So let's calculate the root mean square speed for nitrogen at 25 degrees Celsius. So then, mu is going to be equal to the square root of 3 times R, which is 8.314, times our absolute temperature. We said our temperature was 25 degrees Celsius, so that's going to be 298 Kelvin, all over the molar mass of nitrogen, which is 28.02 grams per mole. But remember, our value for R is giving us kilograms. So we're going to need to change that to kilograms in order to use it in our equation, which will then be 2.8 times 10 to the negative second. And of course, that would be kilograms per mole. And so as we get ready to solve this, let's take a look at how our units cancel. First of all, we have kilograms here in the denominator and kilograms here in the numerator, which will cancel. We also have moles in the numerator and moles in the denominator. We also have Kelvin and Kelvin, and that leaves us with meters squared per second squared after we take the square root of all of this. Then we will end up with our units in meters per second. And when we solve, you get 5.15 times 10 to the second meters per second, which would be 1,150 miles per hour. Since molecular speeds depend on the mass of the molecules, there are a couple of phenomena that can occur. Effusion is the escape of gas molecules through a tiny hole into an evacuated space. Smaller, less massive molecules will effuse much more easily than larger, more massive molecules because the smaller molecules move faster. They have a faster root mean square speed. The faster the molecule is moving, the more likely it is to hit the hole. Diffusion is the spread of one substance through space, like these perfume particles, or through another substance, like food coloring through water. In 1846, Thomas Graham discovered that the diffusion rate of a gas is inversely proportional to the square root of its molar mass. If we look at two gases at the same pressure and temperature in identical containers, we can compare the rates of diffusion. Mathematically, we would express that as R1 over R2, and these are the rates of diffusion of the first gas and the second gas is equal to the square root of the molar mass of the second gas divided by the molar mass of the first gas. One final thought as we finish up with the gas laws. We've talked about ideal gases and ideal gases behavior. We're working under the assumption that the ideal gas molecules don't have any attractive force for each other and that they occupy virtually no volume. In reality, all gases do have some attractive forces and do occupy a finite volume. And since at high temperatures, because of the high amount of kinetic energy, attractive forces between gas particles are pretty minimal. And at low pressures, gases are able to expand, and so therefore gas molecules occupy very little volume. So we say that gases behave ideally at low pressures and high temperatures.